Escape speed. When we throw any object upwards, it obviously falls back on the ground. Larger the speed at which an object is sent out, larger will be its height of ascent. A minimum initial speed of 11.2 kilometers per second is required for the projectile so that it does not fall back on the Earth's surface. This minimum speed is known as the escape speed. We can calculate escape speed of projectiles by using the principle of conservation of energy. Suppose a projectile is launched so that it reaches a point at infinite distance. Let its speed at infinity equal Vf. Therefore, its kinetic energy equals mvf square by 2. Let its total potential energy equal W1. Therefore, its total energy at infinity equals E of infinity equals W1 plus m into Vf square by 2. Suppose the object is thrown from a height h above the ground level with a velocity Vt. Then its energy at the time of leaving equals E of h plus Re equals half mvt square minus gm-me by h plus Re plus W1. According to the law of conservation of energy, the above two energies are equal. That is, mvt square by 2 minus gm-me by h plus Re equals mvf square by 2. As Vf is always larger than 0, the right-hand side of the equation is larger than 0. Therefore, mvt square by 2 minus gm-me by h plus Re greater than or equal to 0. When Vt is minimum, the left-hand side of the above equation is equal to 0. That is, half m into Vt minimum square equals gm-me by h plus Re. Vt is the minimum speed, escape speed required by the object to reach infinity. Special case, if the object is launched from the Earth's surface, h equals 0, and Vt minimum equals under root 2 gme by Re. Using the relation g equals gme by Re square, we get Vt minimum equals root 2 g Re. This expression gives the escape speed for an object to leave the Earth. As g can easily be found by experiment and Re, the Earth's radius, is constant, it is easy to calculate Vt minimum. The escape velocity Vt minimum equals 11.2 kilometers per second. This equation can be applied to Moon as well by substituting the values of g and Re for the Moon. As both g and r are less for the Moon, escape velocity on the Moon is also less and is equal to 2.3 kilometers per second. This is nearly 5 times smaller than that on the Earth. Geostationary and polar satellites. In the previous section, we saw that the time period of an Earth satellite is given by t equals 2 pi into Re plus h by v equals 2 pi into Re plus h whole raised to 3 by 2 by under root of g into me. Any satellite in circular orbit in Earth's equatorial plane such that its time period T is 24 hours, which is the time period of rotation of Earth around its axis, would appear to be stationary when viewed from the Earth. Such a satellite, which is stationary with respect to our Earth, is known as geostationary satellite. For such satellites, Re plus h equals t squared gme by 4 pi square, the whole raised to 1 by 3. In the above equation, when we consider t equals 24 hours, then h equals 35,800 kilometers, which is much larger than Re. Though it requires very powerful rockets to launch satellites at this height, geostationary satellites are launched due to their benefits in areas such as meteorology and remote sensing. Geostationary satellites are used to transmit communication signals, which require a large array of antennas at different places on Earth in a cost-effective manner. Electromagnetic waves above a certain frequency are not reflected by the ionosphere. Radio waves in the 2 MHz to 10 MHz below the critical frequency are reflected by the ionosphere. In other words, the signals cannot reach beyond a certain range. Television and many other communication signals cannot be received beyond the line of sight. Geostationary satellites are used to overcome the above-mentioned barriers. These satellites can receive signals and beam them onto wide areas on the Earth. Government of India began launching its geostationary satellites known as Indian National Satellite, INSAT system satellites in 1983. While geostationary satellites orbit along the equatorial plane, polar satellites, also Earth satellites, orbit in the polar plane, in the direction of the north and south poles of the Earth. These satellites, with a time period of 100 minutes, orbit at low altitudes, in the H approximately equal to 500 to 800 kilometer range. A polar satellite covers one strip of land in the longitudinal direction in one orbit. In the next orbit, it covers the adjacent longitudinal strip, and so on. Thus, it takes an entire day to cover the whole Earth. As polar satellites have low altitude, they give out high-resolution images. Polar satellites can give close-up images of the Earth. Polar satellites are particularly used to study polar and equatorial regions and are used in meteorology, remote sensing, and environmental studies.